Good evening, everyone. Well, I have in front of you a new calculator that I'm going to have a look inside. I've got to admit, I've already opened this up briefly to have a look, so I do have some idea of what I'm running into. And the goal for this moment is just to see if I can get this calculator to work. This is a 1974 era Digi-Matic M8-2. This is, as I understand, a Sears house brand calculator. I don't know who made it, but I'm just looking on the background here so I have some information to give you. This is from calcumuseum.com. Calcumuseum, one word. So they did list this as a date of introduction about 1974 US. They give its requirements and all that. It has a built-in battery charged through a, I don't know what size that is, 1/16 of an inch jack on the back. I don't have the power supply for it. And I've looked in already, and it's got 3 AA size, more or less, nickel cadmium batteries in it, which have leaked fairly badly. But I'm hopeful they haven't damaged the circuit board or whatnot too badly yet. So that's the hope anyway. What my aim is today is to simply get power to it. It looks like it has a step-up circuit of some sort, a buck regulator, assuming they did such things in 1974 in it. So I suspect that the voltage I give it isn't super touchy, but my intention is to use 5 volts from a USB power bank using this, and then to drop it down, about half a volt by just putting a standard diode in there, which on the meter drops it about 0.6 of a volt. On the data sheet for moderate current, about 0.7. My guess is it'll be closer to 0.6 because this is still not going to draw very much. It's supposed to, according to the back, run for 8 hours on 3 AA's. So the next step, assuming I can get this working, the next step will be to replace those batteries with something else and figure out some power supply that's probably not quite so kludged together. I have in my notebook here a few potential, I won't show you yet, just yet, a few potential approaches to that problem. One of the problems that comes in my mind is that 5 volts is not a lot of headroom to put any sort of circuitry in above something like these 3 AAA nickel metal hydride batteries. So my current thought is to put these in, figure out a charging circuit, maybe go for 6, see if I've got a 6 volt power supply kicking around, and then just do a very low current power supply to charge these. Big Clive had a project about a month ago on his site, and that's sort of what I was thinking of doing. So set it up as a really low current charger that it could sit on for weeks without a problem, and then I don't have to think about it very much. The design criteria become fairly straightforward. I'll probably use that diode in that. I mean, other options would be, since it's designed for AA's, and I think there's a fair amount of space, hot glue 3 of these AAA holders inside. And that's the easiest solution. And you can just put in nickel metal hydrides, or even alkalines would probably be fine. Yeah. And the other option, of course, would be to use some sort of active charger. This is just a bog standard, ordered off of eBay, I think. I don't remember. I've had this one for a while. Buck converter. One of these adjusts the current limit, and one of these adjusts the voltage limit. So you can set the voltage limit to, say, 5 volts or something, right? Even higher, maybe even 6. And then set the current limit to, you know, something reasonable. You know, you could almost fit that in there as is, right? But I don't think you could fit that and, you know, the AAAs. But, you know, that's a possibility, right? That would be a full solution to the problem there. So I'm not quite sure what to do. You could also, of course, use a linear regulator. I'm not even sure what this one is. Yeah, it's an LM317. But you could use that in constant current mode and set the current however you wanted. This has the advantage that you could probably cobble together something that would be pretty small, but it's a bit outside my comfort level, I think, to do that. So I think what I'm going to do is something really simple, which will involve a power supply, probably this diode, and or one of the others, and probably a 6-volt power supply. The original power supply for this, which is available on the website that I was looking at, Calcusium, does have a link to the power adapter, which is the Sears power adapter. Let's see, where do I see it here? Number 415. And that doesn't tell me something important like, you know, is it center pin positive on that jack? But it does tell me that it was rated 117 volts, 4.5 volts DC, 150 milliamp hours. Let's have a look inside this calculator. We'll try to clean it up, figure out what is the positive and what's the negative in here, and see if we can get it, see if it'll turn on. That's the plan for tonight. So I'm not going to zoom in too much, at least at this point. As I said, I've had these screws out before, so I didn't put them in very tightly. They were extremely tight when originally put in. It's a bit of a shame that the bottom of the label has come off there. It almost looks like someone had their name on there or something and cut it off. Actually, that's probably exactly what happened. But I mean, even the rubber feet are still nice. This shipped with a case, the battery. Although it's interesting, the battery they show in the image online has a plug in it, which would make life easier. This does not, as you can see. This is soldered in. It's definitely a made-up battery pack, right? Because we've got Japan MIC 054A, and this comes in here without any sort of anything. But what we do now know, right, is we know that this is the positive side, right? That's the positive, that's the negative. So let me get something to mark the positive here. I'll get a red marker. Should have had one of these available. I'll have a red marker. So in fact, it's, I don't know how the plug works, but we'll worry about that after. So this is the positive here. Let me drop that and get red ink on myself here. We'll use the big side of the pen. Okay, so that's the positive there. And in fact, just so you can see, I will zoom in for this. Just so you can see, it's marked positive right here. So I'm actually going to clip the battery off. I'll leave some wires on there. And let's get that out of there. The next thing I'm going to do is get, let's see, steal a sheet of paper out of the printer. Good thing I did. This was obviously half of a coloring page that was shoved inexpertly into the top of the printer. Would have jammed it, but good for my daughter for not wasting. And I'm going to brush off, you see, just with a brush here, all the bits of electrolyte that are in here. My aim at the moment is not to clear this out entirely, but just to get the worst of it under control, because we're going to be in this, sorry, zoom out again, I'm sorry about that. And the white paper probably doesn't improve the, okay, that's off anyway. I've got to say, whoever soldered on here managed to do a pretty good job of melting this jack. In fact, I think this whole jack is done. So whatever we're doing, we're probably putting in a new jack and a few other things. Okay, I don't want to lift this board right now. I will say I also had a look under there before. I will lift it in a minute because I do want to show you something under there though. Okay, so that's the worst of this out of the way. Let's slide that over here. I'll just lift off this board to have a quick look underneath. Yeah, let's do that. So this has 3 screws right here. I'm trying to get myself centered. So we've got 3 screws here. And underneath you can see the main board. I'm going to be very careful because all this stuff is soldered on. We'll just pretend there's not any cadmium in any of this while I brush it around here. I don't know if the metal gets into the electrolyte. I don't think there's actually much cadmium in a nickel cadmium battery. But so, in terms of things that we might be concerned about, this over here, that trace has had some damage. These all look kind of okay. We've got some marking of components on the side, diodes across here, and this is the really interesting thing. So here, this is a bit hard to see. All right, so there's a chip there, there's a chip here. I'm guessing this is the processor. Can I read the number off of that for anyone who might know about such things? LC1552B. Let me write that down. And there's date code, which I can see underneath it. So let me write that down so I can look it up. LC1552B. And the date code is 74. That fits. 1-2, so December of 1974 seems likely. We've got some capacitors, there's a trimmer, and this is the really interesting part. Over here, there's an inductor, there are 2 transistors. I think this might be a step-up circuit to generate the voltage that this needs. If this needs something more like 7 volts, right? And we drive it with a 9-volt battery, most calculators of the era. I don't know. I'm just guessing. That looks like a transistor, maybe that, I don't know. And then we have ITT 508 ITT508N, and it has a date code too, which is 7424. Well, if those are weeks instead of months, that both makes more sense, right? 12th week and 24th week. Okay, that, can we see where the tracks go? That looks like it's a display driver for the LED up here. And the LED looks to be the standard segmented display from the era. I'm just going to get my brush here and just brush out anything that's behind. The keyboard is all down here. I would prefer, that looks like it's all heat staked on. So this is not to be removed and probably not removable. So we're going to hope that no damage got to the keyboard. So my concern is this track here and possibly some of these other traces. Look, there's a pot there. It looks like there was tape over it. So I'm going to guess that this is not the original battery pack. This is a replacement that was soldered in, and the original one did in fact have a cable and a clip and a plug, I mean, because that fell off at some point. Anyway, and that would explain the mess of soldering around here. So we have our positive lead here, and we have our negative there. Excuse me. Definitely allergy circumstances today. So let's get out the meter. We'll need that. Let's put the screws back in for this, and let's make out our very basic circuit that we're going to use here, and I'll show you how it's going to work. But let me put this back in gently. We're not going to tighten anything down entirely because probably won't even put the back on this, because the chances of having to be back in here again are fairly high. But I'm got to say, I'm even nervous spraying a bunch of contact cleaner around in here. If my brushing things, I certainly don't want to go overboard with vinegar and whatnot if it's not necessary. Okay. This screwdriver. So let me just explain how the circuit I'm planning to do will work. Okay, so we've got here a little diode, just a standard 4007, I think. Let me get the meter out. No, zoom down, and you can look at the diode. And what I just want to show you is, how current or the voltage drops over a diode. And the thing about a diode voltage drop is unlike the voltage drop across a resistor. It's not dependent on load, right? So it's not dependent on current. So, or as dependent on current, shall we say. So, okay, here's the diode. And here we can see, when you go forward, the voltage drop is 0.58, 0.59, depending on how well I get the probes on it. Obviously, if you go the other way, there's no voltage because, well, it's a diode. That's what it's supposed to do. Now, this voltage drop is relatively insensitive to It's relatively insensitive to the current. It isn't entirely, but it's relatively insensitive to the current. So you can use this, or I'm going to use it, as a way to try and limit the voltage coming from this power bank, through these leads. And what we'll do is we'll press that on. Well, here, I'll cut the meter again so you can see how it works. I'll put that on. I'm going to put on the negative this way, so that should point towards the negative, and I'll explain why I'm doing it on the negative. That's just for convenience. And let's not short out the power bank. Okay, so here we've got the meter. We'll put it on voltage, DC. Okay, so if we go, you see both of those? Yeah, that works. So if we go from positive, we'll see about 5 volts, right? This is one of these real cheapy, this is actually a literal dollar store, power bank, these kind, right? And the advantage of this is it always supplies power. So, from one end to the other, this one's pretty good actually in terms of voltage. So it's 5 volts pretty well on. Now we'll try to the other end of the diode. .8, right? Again, there's no load on it. So we've already had some voltage drop to 4.8, and you put a little bit of load on it, you'll get something that looks more like the 0.5 that the meter calculated. So this is what we're using the diode for. And the diode also, of course, would protect the calculator and the batteries and whatnot from someone plugging someone in the wrong way. So let's unplug the power supply. I'll leave that there. So what I'm going to do is I'm going to try to retin that lead. And I'm going to solder this diode. As you'll see, this is all connected together here. That forms the, I don't know if you can see, but it forms the negative. If I can pull this insulation off, I might have some relatively new wire to solder to. Again, we might be in trouble because of the usual problem of the oxide making its way up, these sorts of things. In fact, I'm going to clip this off. Oh, sold insulation is tough. Yeah, that doesn't look too bad. So we'll tin that, and then we'll be able to clip in here and there. Let me get the soldering iron out, hopefully without injuring myself in the process, always. There's just too many wires around here. Okay, so let's start by tinning this. Yeah, you see it's really not tinning, right? Okay. I'll give it a little bit more flux. I mean, if it's a problem, I will replace this wire. It's starting to get somewhere. Let's try a little bit of. Well, I'll just try that for now. Now the second thing we want to do is we want to try to tin this. not going to muck around. We're just going to dump a whole lot of flux on that right from the start. Okay. Again, this doesn't have to be great. This is just proof of concept here. But it does have to be better than that. Let me turn the iron up a little bit. That's shoddy by my standards. That's pretty shoddy. Okay, let's get this off, and we'll try to do it directly to the post. Now, you know what? Let's screw all that. Let's do it this way. There we go. Okay, so there's the negative, and there's the positive. Now, assuming we've actually got any continuity there, again, I'll pop out the meter, put it into continuity, untangle the probes. Don't know if it'll do continuity through here. Let's find out. Okay, we have continuity from here to here. All right, do we have continuity from here to here? Yep. Okay, let's just go to Diode Check, make sure I got the diode on the right way. Always a potential issue. Yes. Okay, so that means that we should be able to power this calculator. So I'm just going to bring these leads in from the sides with some care. I should note that assuming I have the diode on the right way, oh, these things are really terrible. Okay, and this one will come in. Okay, we were trying to come in from the other side so it wouldn't risk anything. Okay. Off. All right. Okay, I got a low power warning on the camera, so hopefully nothing's blown up. So let's try it. Okay, so I'm turning it on. And I'm getting a flash. It's drawing current, but it's not turning on. So that leads to an interesting question. How much current is it drawing? And I will be right back. I'm going to go find a USB current meter. One of the nice things about using USB for this sort of stuff is that you've got USB current meters. Okay. So 5.8 volts, 0.01 amps. So it's drawing nothing with the power switch off. Power switch on, 0.05 amps. Okay, we have clear. Where's clear? Clear, clear. Clear. Okay, so this is interesting. 1, 2, 3, 4, 5, 6, 7, 8, 9. We're missing one segment here. Is no good. But times 2 equals, right, overload. It works. So what do we know? Let's unplug this. We know we've got power. We know that we have a reasonably effective power solution. And we also know that there is something that is preventing this segment of the LCD from working. Let's zoom in and we'll see. I think we may know what that is without even looking at it any farther. If you zoom right down here, so this is the LCD, right? The rightmost segment is bad. And look at that trace. It's the worst one on the board. So let's beep that out a little bit and see if it's in fact bad. If it is, we'll put a bodge wire on that and see how we're doing. Okay, so here we have the meter, back in ohms, back in, all right, so we got continuity. So we're going from here, it's a dry solder joint if nothing else. So let's go from here, that goes all the way along here. If we so we got nothing, right? If we try this one goes to the third pin, I think. Yeah. Right? So, I mean, that looks like a dry solder joint, but I don't think that's what the problem is. I think the problem is probably that trace is eaten up. So let's make ourselves a little wire bodge. So I think that's a little long. All right, so let's strip this one there. Okay, so it was this one, goes all the way down through there to here. So let's turn down the heat on the iron a little bit. Okay, so we got that done. Let's put a little bit of, this is where I wish I had a smaller tip on the iron, but that's okay. Well, that it wasn't quite so hot. Okay, I'll bring this over here. All right, so we've got that there. We need to bring it up. Oh, did I cut it too short? Almost. We're going to make it. Okay, that's what we're going to do here. So let's pull that out of the way. We'll give this a touch of solder. I definitely have the iron too hot now, so I won't touch anything. Okay, we've got a little bit of the same problem we had with some of this other stuff, in that this is not taking solder as well as it ought to. I'm really nervous about putting a lot of heat on that. Well, let's leave it like that for the moment. Yeah, I don't like that at all. You see what the problem is? The problem is that I was trying to say the problem is that okay, that looks like it's making contact. Okay, let's leave that like that for now. Let's get everything out of here. Let's get this back into play. So we'll clip in. Right, keeping in mind that we can't destroy it because we have the power of a diode. Okay, so we're going to plug in. Here's our, oops. And there we go. I don't know if you can see this. Let's zoom in. This is a very nice display. So 2 times 2 equals 4, 8, 16, 32. Okay, clear. Mem plus. Oh, there's the memory light. I don't know what D does. Memory clear, that goes away. Equal K exponent. Oh, I don't know what that does. I might have to find a manual. Anyway, but we have a 4-banger calculator with a few extra features. We have, at the moment, a workable alternative USB power supply that seems to make this work. And it's a working calculator with one little bodge wire right there. So I'm going to put this away for today. I'm going to think about possible solutions to this battery issue, but I'm extremely pleased with this. It works the power issue can be solved in a number of ways. Well, I will put this away and I will probably come back and then we'll see how I've decided to deal with the power problem after.